were there any that you just like, once you read it really well, were there any that you were just like eliminated immediately? C and D? Yeah, C and D. There's a lot going on there. And I guess if you looked at this, if you looked at the phrase proportional to the amount that's present, the C and D, both of these, the proportionality is really with more than just the amount that's there. There's a lot of extra stuff. And the truth is, C is actually something. It's not anything that we'll cover in our class, but it is something that if you took BC or Calc 2 later on, you'd find out that that actually is something. But if you guys did eliminate C and D, you were definitely right to do that here. It comes down to A or B. Which one did you pick? Oh, frozen. No, not. Okay, so it came down to A or B. Which one did you guys pick? A is right. A is definitely right. So this is saying that the rate is proportional to the amount that's present. How would you guys describe B? If it said, you say the rate is proportional to time. And that could be something, but it's certainly not proportional to the amount present. So anyways, so A would be the correct answer for number 3. For number 4 says the rate of change of the number of bunny rabbits in a field is proportional to the number of bunnies in the field. So again, you look for that familiar wording. The rate of change is proportional to the amount or the number of things, in this case bunnies. Which equation describes this relationship? And so these are not differential equations, right? These would be like solution curves. And so which one did you pick? Did you guys pick B? B, so this one right here. Now this would be the familiar, certainly the more familiar format from pre-calc. So of these two, I would say that the formatting of 3, as far as asking you about differential equations, would probably be the one that you'd be quizzed on, right? Because somebody in pre-calc might be able to handle number 4 with absolutely no knowledge whatsoever of calculus. So maybe number 3 would be the what you might expect, like that sort of question, at least on those sorts of topics. Okay, we good? Yes? All right, so then in the video, you guys saw an example about bacteria. I thought here in class today we'd do one example having to do with radioactive decay. And there's a terminology in here that I want to make sure we all understand that we can use here. I'll read it out loud, and we'll talk about the term. It says, a substance decays at a rate proportional to the amount present. If 30% of such a substance remains after 16 years, what is the half-life of the substance? So half-life, if you've had some science class that dealt with this, maybe chemistry would be maybe a typical one that talks about half-life. Does anybody know what half-life is?
How long it takes for the substance to decay from half its original mass.
Okay, so how long it takes the substance to decay to half its original mass, what you said. Okay, good. So he said how long, so what kind of a unit would go with half-life? It's a time unit, yeah, so like minutes, years, hours, seconds, whatever. Yeah, so this is, I'll write it out here. It is the time needed for the substance to decay to half of its original amount. Sorry, I just misused its. Doesn't that drive you guys crazy? Does its get an apostrophe or not? Or do you care? Maybe you don't care. Huh. I actually get marked off on my graduate papers if I have grammatical errors, so I've returned to my grammar precision, or I still don't know how to do a semicolon, but whatever. Okay, so time needed for a substance to decay to half of its original amount. All right, so if you did okay with the bacteria question in the video, you might be able to handle this one. So I want to give you a chance to kind of work through this, work through it together as needed, come up with solutions, come up with questions, and we'll revisit this and go through a solution here in just a second. What's true about this? Did you guys, I'm sure you heard me say this, decays at a rate proportional to the amount present. That's the key wording that tells you that you've got exponential growth or decay. And so from that, if I use the letter S for the amount of substance, is that okay? S? So I would say, based on that, I'd write a differential equation of ds dt is equal to ks. ds dt equals ks. You want to recognize that differential equation, write it down. And then if you remember from the video, there's no requirement typically, unless it uses the magic words of like, find the particular solution, separate the variables. If it doesn't use that kind of language, then you can just jump to the solution curve, right? So the solution curve for this would be, you could write this out as like S equals CE to the KT. And I'm going to erase this stuff here in a second, but it's really important for us to remember what these things stand for. So S stands for the amount that is there, the amount that is present at any particular time. So S would stand for the amount that's there when t equals 0, or you could say when t equals 10, or t equals 16, or t equals 20. S just stands for the amount that's there at any particular time. Do you guys remember what C stands for? So C is a constant, but in the context, the initial amount, or the beginning amount. Yeah, so initial amount. So the C is going to be what it is, but the S is going to be moving up or down as time changes, because it's, whatever it is growing or decaying. Of course, T stands for time. K is the constant of proportionality that tells you how fast it's decaying or how fast it's growing. So I wanted to make sure we are all right here. Do you guys have any questions about this so far? Okay. So as I've walked around and kind of like talked to you and just watched what you're doing, definitely struggling with what do we do with the 30%? What do we do with the 16? Obviously, that's, I think obviously it's going to be a help, or it's intended to be a help for us. Can I give you guys a couple more minutes to kind of wrestle around with this a little bit, see if you come up with something good? So hopefully we're all there. If we weren't all there, maybe now we are. See what we can do with the rest of it. This phrase right here, here's my thought. You can tell me what you think about this if you want. It says 30% remains after 16 years. And so this doesn't give you like 30 grams or 30 pounds or 30 ounces, whatever it is. It says 30% remains after 16 years. So to me, it's pretty clear that we would plug in a 16 for the t value. So k times 16. But then what I'm thinking is, to figure out this 30%, if I divided both sides by c, I would get the amount that's there divided by the amount that was there to begin with, right? And if I take the amount that's there divided by the amount that's was there to begin with, wouldn't that be 30%? Like take what's there, divide it by how much was there to begin with, and according to this, that after 16 years, that ratio, or that percent, would be 30%. So 0.3 equals e to the 16k. Does that seem logical to you guys? Just take s divided by c and replace it with 0.3. From here to get the k by itself, we'd have to go ln of both sides. That would then give me natural log of 0.3 is equal to 16k, dividing both sides by 16. I would get this right here, and this would be a word of caution to you as far as rounding stuff goes. I'm sure that ln of 0.3 over 16 for the k value, I'm sure that that's some long, unpleasant decimal. If you round it off early and then you use that rounded off version later, you're going to be off. And you have to be right on. This is one of those things where it could be frustrating because you'd be like, hey, I'm only 1,000th off or whatever. It needs to be right on the money. There is a wrong answer and there is a right answer. It's got to be the right answer. So something you could do if you wanted, you could do this. S is equal to C e to the ln of 0.3 over 16t. You could just put the k value in there as is, right, without doing the decimal thing. You can, of course, store the decimal in your calculator and just use it later, whatever. Just don't use the rounded off version later on. Make sense? Okay. So then I think I would follow a really similar strategy when it comes to the question, what is the half-life of the substance? I would, again, divide both sides by c. So I'd get S over C equals e to the kt. I'm just writing k because I already know what my k is. I'm just writing it because it's faster this way. In this case, if I'm looking for half-life, what would the S over C ratio be? It'd be 0.5. It'd be half, yeah. So we could write 0.5 is equal to e to the kt. I'm looking for t this time. And so what I'm going to do is ln of, oops, let's put my equal sign there. E to the kt, so I'm going to do ln of both sides, so it's going to be ln of 0.5 equals ln of e to the kt. And my final couple of steps should feel kind of like the other ones. So it's going to be natural log of 0.5 is equal to kt, divide both sides by k, and my k is this right here. And if you do all that, ln of 0.5 divided by ln of 0.3 divided by 16, it's that 9.2 something number, right? Am I right? That's the number I saw floating around a lot. I think that's right, 9.211. So 9.211 units for that. Years is equal to t. Does that make sense in the context of the question? If 30% is left after 16 years, wouldn't there be 50% left in less than 16 years? So hopefully that makes sense in the context of the question. Do you guys have any follow-ups for me? No questions? Okay. If there's nothing else, I agree, Ben, 6.3, here we come. Let me give you room. Alex, you look like you might have a question. Are you sure?
Yeah.
Okay. Riley, you good?
Yeah.
You said you got stuck on one part, but you're okay now?
Just like the 0.5 part, I'm good now.
Okay. All right, go ahead and flip over to 6.3. We'll take about 15 minutes, do a little work here in 6.3. So give us a good start for tomorrow. Okay, so this is it. This is probably, like I mentioned before, this one is probably in the top 3 or 4 of like most important sections in the year for out of our book. So let's review a little bit. If you're going to be solving a differential equation, what is your first step? Separate the variables first. That's right. So if you remember from before, this is the step where if you do not show this on your paper, you are not allowed to get any points at all, which is a really brutal thing. It's how you'll be judged in May. But it also goes to the question of what the antiderivative actually is, what the indefinite integral does, and so it actually is kind of an important step. So we've done a lot of stuff like this before. I think you're going to find, surprisingly enough, on some of these questions, one, it won't be the most difficult thing, but one of the difficult things is going to be to correctly separate the variables. The reason why I say that is because this will involve, in some cases, some relatively heavy-duty algebra. Relatively speaking, I don't know if you're going to find it to be heavy-duty or not, but we'll see. We'll see. So number 1 says dy dx equals 3x squared over y. The instructions say find the general solution, and remember to show the separation of variables. So if you guys would, let's just do this one step. Okay, let's really chunk this down into tiny steps. For number 1, will you please try to separate the variables and see how it goes? Okay, so once you have that, just sit there for a second. We'll check all of our work, and we'll see if we can kind of go from there. Okay, so separate the variables, step 1. Sir. I don't remember. We'll get there. Oh, for which one are you looking at?
2.
For 2. Gotcha. Gotcha. We'll get there.
And then you make that.
Okay, step number 1 for number 1. Any volunteers as far as what you think this should look like with the separation of variables? Volunteers, come on. Anybody? Silence. Hi, Johnny. He's got his mouth full, though. Anybody with not food in their mouth? Josiah. Sorry, Johnny. He's being polite. He's a good man.
I got y times dy and is equal to 3x squared dx.
What'd you do to get that?
I multiplied the y multiplied each side by y, and then multiplied by the x on both sides.
Yeah. That's good description. He's got it right. Definitely got it right. Did anybody just think of this as like a cross multiplication? That doesn't always work, but in this case it does. It's a worthy strategy. So Josiah and perhaps you are all on the right start here as far as this goes. Again, I want to emphasize, please understand this. I want to emphasize as far as scoring and understanding goes, what I'm about to write is wrong. It looks sort of close, but this would earn you nothing. And so take your time and go slow. Watch this. What if I wrote this? Instead of y times dy, what if I wrote it as dy over y?
Wrong.
I can see how someone would do that. That's definitely wrong. And you look at this and say, did you really separate the variables? Not really, not with a valid method. And so you would likely be looking at nothing here as far as points go. So please take your time and just do it right. And I don't think you'll have anything to worry about. It's not like you don't know how to do it. You just need to do it right. Okay? Johnny, question?
Would you still get all the points if you already just wrote the integral of y dy equals?
Say one more time.
Would you still get the points if you had an integral of y times dy?
Oh,
Equals,
absolutely. You know what? Let's talk about that. We'll talk about it right here. So if you did correctly separate the variables, congratulations, you just earned a point, and a big point, right? That's really important. Once you have separated the variables, if you remember this from back in chapter 4, after you've done this, what do you do next? Integrate. Yeah, we're finding antiderivatives. And so what Johnny asked about was if this is our step, like if this is just sort of our first step where you insert the integrals in here, would this still count as the separating of variables? Definitely. Definitely would. So you don't, I mean, if you want to show 2 separate steps for these, no problem, but you don't have to do that. Okay? See if you can take it home. Okay? See if you can bring this one home. We're looking for antiderivatives. We're looking for a general solution. So ready, set, go. Antiderivative of y is 1/2 y squared. The antiderivative of 3x squared is x cubed, and then plus c. Noah and I were just talking about the c here, and really the good question of why there isn't a plus c right there. Technically there is, right? But when we think about the c on the left and the c on the right, if I were to combine them by maybe subtracting one from the other, wouldn't I just get some other c? And so the customary practice is to simply write the plus c on the side with the independent variable. So I would suggest you go with like the customary way of doing things. So to finish this one off, we just need to multiply everything through by 2. So you get y squared is equal to 2x cubed, technically plus 2c, but we're going to kind of follow the same sort of principle that 2 times an unknown constant is just some other unknown constant. And so if in your next step, if you wanted to write something like y squared is equal to 2x cubed plus c, it's a different c. And we talked a little bit about how you could note that it's a different c. I'm not too worried about it. If we get our timing right later on, we're going to be okay either way. And then your final step would be to solve for y. So y equals plus or minus square root of 2x cubed plus c. Okay. Any questions? Okay, so let's do our one last one here, number 2. Dy dx equals 6y squared, parentheses, x squared minus 3. Want to give you guys maybe just a minute here to see if you can separate the variables. I'm going to try to show you what, in my opinion, is the most effective way to separate the variables, because I think there's a couple ways you could do it, and we'll proceed from there. So take a minute, try to just separate the variables only for number 2.